If you keep fish, you've probably been told that live plants are good for your water quality. And that's true. But I'd be willing to bet that the reason you've been given, or the reason you think you understand, is wrong. The story most of us were taught goes something like this. Fish produce waste, bacteria in your filter convert that waste into nitrate, and then your plants absorb that nitrate. Plants at the end of the chain, tidying everything up. It's a tidy explanation. It's also a significant oversimplification. And when you actually look at the published research, what aquatic plants are doing to your water chemistry is considerably more interesting and more useful than that. Today, I want to go through what the science actually says about how plants clean your tank, which species do it best, and why not all plants are equal when it comes to water quality. We'll be citing real papers throughout, and as always, I'll have everything linked in the description below. I've also got a book giveaway at the end of the video. 3 copies are going to be given out, so stick around for that. Let's get into it. Let's begin with the nitrogen cycle, because this is where the misunderstanding begins. Fish produce ammonia, which is then converted to nitrite by Nitrosomonas bacteria. Nitrite is then converted to nitrate by Nitrobacter bacteria. And then, as the story goes, plants consume the nitrate. That's the cycle as it's typically represented in the hobby, and it's the version most fish keeping resources still teach. The problem is that it implies plants are primarily nitrate consumers. And when you actually look at the experimental literature on aquatic plant nitrogen uptake, that turns out not to be the case. Diana Walstad, who wrote what is probably the most rigorous book on the planted aquarium from a scientific standpoint, Ecology of the Planted Aquarium, reviewed the published literature on nitrogen uptake across aquatic plant species. What she found was striking. Of 33 aquatic plant species studied in the literature, only 4 preferred nitrates. The remaining 29 preferred ammonium, and not by a small margin. Think about what that means practically. Ammonia, or more precisely ammonium in its ionized form, is what fish are producing directly. And the research suggests that plants are competing with your filter bacteria for that compound, not just mopping up what's left at the end. Walstad cites studies on duckweed, Lemna gibba, which removed 50% of the available ammonium from a solution within 5 hours. And this was in a solution containing over 100 times more nitrate than ammonium. The plants barely touched the nitrate until the ammonium was gone. A similar pattern was found in Elodea nuttallii, one of the most common submerged aquatic plants. In a mixed ammonium and nitrate solution, it removed 75% of ammonium within 16 hours, while leaving the nitrates almost entirely untouched. Only when the ammonium was depleted did it start seriously taking up nitrate. There's also some very clear data from studies on water lettuce, Pistia stratiotes. Plants placed in a solution of nitrate took 18 hours to absorb the nitrogen. The equivalent amount of ammonium was absorbed in under 4 hours. When researchers increased the nitrogen concentration, the gap widened dramatically. Nitrate uptake took 71 hours, whereas ammonia uptake still only took 4. The biochemistry underpinning this makes sense when you think about it. All plants use nitrogen in the form of ammonium to synthesize their amino acids and proteins. If they take up nitrate, they have to reduce it to ammonium first, which costs energy. Taking up ammonium directly skips that step, so it's not surprising that plants prefer the more efficient route when they have a choice. What this means for you as a fish keeper is significant. A heavily planted tank isn't just absorbing nitrate at the end of the cycle. It's competing for ammonium at the start of the cycle, before the nitrifying bacteria even get to it. That is a meaningful distinction, and it changes how we should think about what plants are actually contributing to water quality. It also means that nitrate can still accumulate in a well-planted tank, because if ammonium is being taken up efficiently, there may be less of it available for bacteria to convert to nitrate in the first place. So the relationship between plant density and your nitrate readings is more complex than the simple model suggests. That context established, let's talk about what plants are best for water quality, because not all plants are equal here, and the research is fairly clear on what matters most. The primary driver of how much a plant contributes to water quality is its growth rate. Plants take up nitrogen, whether ammonium or nitrate, as part of building biomass. More growth means more nitrogen removed from the water. It's really as simple as that. There's a really useful 2020 study by Manalaki and colleagues published in a peer-reviewed journal and available on PubMed that compared nutrient uptake kinetics across 12 submerged and 7 amphibious plants. They measured maximum uptake rates for ammonium, nitrate, and phosphate, and looked at how these related to relative growth rate across all those species. One of their key findings was that fully submerged species had significantly higher ammonium uptake rates than amphibious species, which is interesting because it suggests that the plants we keep fully underwater, your stem plants, your floaters, your mosses, are better positioned to absorb the most harmful nitrogen compound directly from the water column than plants with emergent growth. The other important distinction, and this is something experienced plant tank hobbyists know well, but it's worth grounding in the science, is stem plants versus root feeding plants. Stem plants and floating species absorb nutrients directly through their leaves and stems from the water column. Root feeding plants, your cryptocorin species, your echinodorus, take up a significant portion of their nutrients from the substrate layer. So a root feeding plant may be growing well, but drawing much of its nitrogen from the substrate rather than the water itself. For water quality purposes, water column feeders are going to have a more direct and immediate impact on your dissolved nitrogen levels. That doesn't mean root feeding plants have no value. They absolutely do, especially in soil setups. But if your goal is specifically to reduce ammonia and nitrate in the water, fast-growing stem plants and floaters are where the action is. No disrespect to cryptocorin, it's still my favorite species. There's a really useful study I want to highlight here because it's one of the few pieces of research conducted specifically in aquarium conditions rather than in lakes or constructed wetlands, which is a distinction worth making because most of the macrophyte literature is dealing with very different water volumes and conditions than a home aquarium. Csontos and colleagues published in 2024 in the North American Journal of Aquaculture compared two floating aquatic plant species, Najas grass and Java moss. In aquariums stocked with endler guppies, Poecilia wingei, the study ran for 4 weeks and measured nitrate and phosphate weekly. The control tanks, fish but no plants, saw nitrate climb to around 33 to 35 milligrams per litre by week 4. The tanks containing Najas grass only reached 8.75 to 11.5 milligrams per litre. It's a substantial difference from a plant that doesn't require any substrate, no CO2, and minimal light intensity. Java moss performed well too, keeping nitrate lower than the controls, but Najas consistently outperformed it. And when the researchers looked at why, the biomass data told the story. Najas showed a 1.6-fold increase in biomass over the study period compared to a 1.2-fold increase from Java moss. Faster growth, more nitrogen removed, exactly what the underlying biology would predict. Phosphate followed a similar pattern. Control tanks reached around 2.4 milligrams per litre of phosphate by week 4. Najas tanks stayed around 1.05 milligrams per litre, less than half. Phosphate is often overlooked in water quality conversation, but it's a significant driver of algae growth. So this is a meaningful finding. Now, it's worth being transparent about the limitations here. This is a 4-week study in a controlled research setting, and the stocking density and tank conditions may not perfectly reflect your setup at home. But the directional finding is consistent with what the broader literature on macrophyte nutrient uptake would predict. And it gives us actual numbers from an aquarium context, which is rare. So let's make this practical. If your goal is water quality, here's how I'd think about plant selection based on what the science tells us. At the top end for water quality impact, you want fast growing water column feeders. Najas grass is probably the standout based on the Csontos 2024 data and its extraordinary growth rate. It's not the most glamorous plant, but it's arguably the most effective. Formwort, or Ceratophyllum demersum, is in a similar bracket. Fast growing, fully submerged, no roots, absorbs nutrients entirely from the water column. It's also been studied in research for ammonium tolerance and has a track record in the hobby for exactly this kind of application. Floating plants are another category worth highlighting. Duckweed, Lemna minor or Lemna gibba, has some of the most impressive ammonium uptake rates in the literature. As we saw earlier, the trade-off is that it can take over the surface quickly and requires a significant amount of maintenance. Salvinia species are a more controllable alternative. Both are worth considering if you want to maximize water column impact without having to worry about substrate or CO2. Water Sprite and Pistia stellatus are 2 stem plants that come up consistently in discussion about fast-growing, high-uptake species. These are the plants that will visibly need trimming week on week in a well-lit tank, and the fast turnover of biomass is exactly what you want for sustained nitrogen removal. Step below that, you have your medium growth stem plants and mosses. Java moss, Taxophyllum biberi, as we've seen, does contribute meaningfully to water quality. It's slower than Najas, but it's extremely hardy and will grow in conditions where more demanding species struggle. It's a good choice for lower tech setups where you need some plant cover without complex lighting and fertilizer regimes. At the lower end for water quality impact, though perfectly valid plants for plenty of other reasons, are your slow growing root feeders. Cryptocorin species, Echinodorus, these are excellent aquascaping plants that your fish will appreciate. And in a soil-based setup, they can look stunning, but they grow slowly and draw heavily from the substrate. So don't expect them to move the needle on your ammonia or nitrate readings in the way that a bank of fast-growing stems will. This goes the same for your epiphyte species that do draw from the water column, but they are just so slow growing, it really doesn't have a significant impact compared to your faster growing stem plants. It's not a reason not to keep them, it's just an honest assessment of their role in the system. There's one more practical caveat I want to flag just before we wrap up, because it's something that catches people out. Plants only continue receiving nitrogen from the water while they're actively growing. And if you let plants die back, or you don't remove trimmings from the tank, the dead plant matter decomposes and releases ammonia back into the water. You're essentially undoing what the plants did. This is especially important for fast-growing stem species. Hornwort, for example, is notorious for shedding needles when it's stressed or transitioning. If those needles aren't siphoned out or removed, they will decompose. The same applies to any plant that's struggling. A dying plant in your tank is actively contributing to your nitrogen load, not reducing it. So the maintenance of a heavily planted tank matters as much as the plant selection. Regular trimming, removal of dead material, and keeping your plants in genuinely healthy growth, all part of the equation. A tank full of struggling plants isn't cleaning your water, it's adding to the problem. So to summarize what the science actually tells us. First, plants don't primarily consume nitrate. The majority of aquatic plant species prefer ammonium and remove it rapidly, directly competing with your filter bacteria from the start of the nitrogen cycle. That's more powerful and more immediately beneficial than the simple model gives plants credit for. Second, growth rate is the key variable. The faster a plant grows, the more nitrogen it removes. Fast-growing water column feeders, Najas, hornwort, floating plants, fast stem plants are your most effective tools for water quality. Third, not all plants are created equal, and that's fine. Slow-growing root feeders have their place in a planted aquarium, but if water quality is your priority, they shouldn't be the only thing you're relying on. And fourth, plant health and maintenance matter. Healthy, actively growing plants remove nitrogen. Dying, decomposing plants add it back. All of the papers cited in this video are linked in the description below. I'd particularly recommend Diana Walstad's book, Ecology of the Planted Aquarium, if you wanted a deeper dive on this. It's probably the most thorough scientific treatment of the planted aquarium written for a hobbyist audience, and it holds up really well. I also wanted to mention another book that sits very naturally alongside this topic. A while back, I was contacted by Oliver Jameson, who wrote How to Create an Organic Aquarium. We actually started working on a collaborative video based on the book, and for various reasons, the video never made it to the channel, which I genuinely felt bad about because the book is excellent. It covers a lot of what we've been talking about today from a very practical angle. The organic substrate methods, how plants interact with soil biology, and a lot of the applied Walstad principles in a very accessible format. If you're interested in taking a more natural approach to the planted aquarium, it's well worth a read. So as a small way of putting that right, I'm going to be giving away 3 copies. To enter, just leave a comment on the end of this video telling me which plant you're planning to try in your setup based on what you've watched today. I'll pick 3 winners at random and I'll get the book sent out to you. The competition is running to the end of April and I'll announce the winners at the beginning of May. And if you really want to see the unfinished edit of the tank that I was setting up, I put it over in the members channel. It's rough and it never got properly finished. It's a relatively interesting look at the practical applications of Oliver's book. So if you're a member, go and have a look, and if you want to sign up, it's a couple of quid, and it really helps out the channel. So if you found this video useful, then do think about subscribing and liking. It makes a genuine difference to the channel, and I'd really appreciate it if you could share this with anyone who enjoys planted aquariums. And if you've got any questions, then come down to the shop and find us. We're based at Finchley Nurseries, London, NW7 1AS, or you can drop us a message in the comments below. But for now, that's all from me here at Pond Life Aquatics, and I hope you'll join me again next time for this Pond Life.